Okay, hi everyone. Sorry I couldn't be there. This is Baris. I'm an incoming professor in the Allen School starting next fall. And together with David, we'll talk about silent data corruptions and their rise in the cloud and what the FOCI Center can do about that. So what are silent data corruptions? CPU cores, turns out, do not always operate correctly due to electrical defects. So these could be things like imperfections in the manufacturing process or decay of some components over time due to exposure to external stimuli. So this could be phenomena such as electron migration and other things. So the problem with silent data corruptions or silent data errors, as some call it, is that they make CPUs less fail-stop, right? The fail-stop model is something we're used to. It's a nice model where we have pretty efficient ways to understand it and to deal with it without introducing undue overhead. But the problem with SDCs is that they can be quite unpredictable, right? So they may influence software in unexpected ways. So basically, an otherwise well-behaving CPU can all of a sudden become defective at any time, in any location, with any misbehavior. And these corruptions actually may develop over time, right? So this can actually impact you, at some point that's totally unexpected. So major data center operators, including Google, also major cloud operator, of course, clearly established silent data corruptions as a major problem in some of their recent publications, right? So this is just quoting from this recent HotOS paper that Google published, where they observed on the order of a few mercurial cores. So this is the terminology that the paper used to refer to cores that have silent data corruptions. So on the order of few mercurial cores per several thousand machines, and that's turns out similar to the rates that are reported by Facebook. This is a serious enough problem that Google devoted many engineer decades to it already. And there's also sort of extra costs that are just due to loss of availability, right? So besides the people who are spending software engineering hours on the problem, there's sort of additional issues there, right? So if you lose availability, that has impacts on how your products are being used, and so that can have further negative consequences. And again, Facebook observed these at scale, and the rates are on the order of one fault within 1,000 devices. So that's not extremely frequent, but it is not that infrequent that it can be ignored. So, well, the question is, like, why are these silent data corruptions more prominent today, right? So with these kinds of phenomena, right, electron migration, et cetera, these are things we know. Issues in manufacturing, we know about them as well. Let me just, I realize I did not have video on. Okay. So this is really driven by two things. So first one is that process densities are increasing, right? So this is driven by the need to increase compute capacity per given chip area. And smaller future sizes that we've reached is actually making it difficult to manage current and voltage leaks. So that's one thing. The other thing there, again, with process densities, is we do have more elaborate computational structures, right? So we're thinking about things like something to compute a hash or do vector processing. So those can also be more error prone, right? So we have special instructions for these complex operations. So that's sort of with the process densities. The other thing is the scale of observation is increasing as well. So data center operators have visibility into millions and millions of cores. And with the failure rate such as 1 in 1,000, it's no surprise that they're able to observe many, many failures that impact availability. So in the context of FOCI, we want to take a sort of threefold approach to dealing with silent data corruptions. So we're going to focus on detection, right? So these are proactive detection regimes that we want to develop. Mitigation, of course, if we can't detect, can we harden software against silent data corruptions? And then finally, something that's at least so far not has been explored as much is studying implications, security implications of what appears to be a reliability problem, right? And this will be familiar with things like row hammer, right? So bit flips are or were thought of as a reliability problem, but they can be actually repurposed to become a security issue as well. So is there something similar there, similar concern there with silent data corruptions? That's something we want to explore. So I'll talk about detection a little bit. So detecting silent data corruptions before impact is particularly important because it turns out that the cost of dealing with a silent data corruption increases exponentially the later it is detected. So with the detection when the user finds out about it being the worst case. So ideally, you do the testing at design and fabrication time, but this may not necessarily be feasible, right? So you want to try to catch things as much as possible during that time, but that may not work. So the next best thing is testing in situ, where this is sort of in runtime deployments, right? So at the high level, when you're actually doing the testing in deployments, you want to leverage certain things, so such as using knowledge from community, the research that we do, or other tools that CPU manufacturers release for testing their CPUs against bugs, right? So Intel and AMD have both been pretty proactive about engaging with the research community, and they've been already providing access to machines that have silent data corruptions and tools that can detect these kinds of issues. But the goal there is really to build lightweight checkers that you can actually deploy in production systems, right? So that you can scan for issues. So I think there's a lot of interesting research to be done about how, for instance, we can leverage existing programs that are already deployed to do such testing. And then, of course, you want to note the deltas between errors at deployment time and errors that occur over time, right? As a result of silicon rot, right? And so to get further insights about silent data corruption. So what structures or what kinds of functionalities impacted over time, as opposed to what kind of bugs are detected before deployment. So real quick about detection. So a key problem with detection is, if you look at the existing approaches, they're pretty high overhead. So there's fuzzing-based methods, right? There's a fuzzer from Google called SillyFuzz. It generates test cases automatically and it has high defect coverage. It's intended to find silent data corruptions. It generates many test cases, right? Even for testing limited functionality. So it can be really too much for runtime testing. It is comprehensive, but it is pretty heavyweight. You can also use other hardware techniques, such as scan-based methods. So this example, you have a bunch of flip-flops, that's scan flip-flops below. So you can sort of enable them with this different values, right? So you set them to be different values, and they do test parts of the combinational logic. And then you continue actually changing these inputs to test different kind of logic. So it's a little bit like fuzzing with hardware. And the problem with this is, they may actually take a long time to execute. So they're also not very suitable for runtime. So we want these tests to be small enough, but how are we going to get there? So I'll talk about just a few insights that we have towards allowing that. The first insight is that we can have, we know that actually defective cores tend to have consistent misbehaviors. So this is just, from interacting with CPU vendors and available documentation, we know this. So this means that we can tailor test cases to CPUs and deploy them on different CPUs. And this tailoring can also be CPU specific, right? So if we know certain error-prone features are supported by the CPU, that might allow us to tailor the tests, for instance. Another insight we have is that some of these data corruptions are easier to detect under low voltage settings. People have actually used this kind of insight to develop different kinds of attacks. but we can deliberately operate CPUs under low voltage and find so-called weak registers, right? So these are really the weak flip-flops, if you will. We can then use this kind of information to guide test case synthesis that we would later deploy in a production setting, right? So there's, again, sort of a programming languages and software engineering aspect of like, how can you synthesize minimal, compact enough test cases that will exercise a particular set of weak registers in a meaningful instruction sequence. That's an interesting research problem. And then finally, you can actually use the program itself for testing, right? So the programs are going to be deployed in production, running in millions of cores and so on, and you can leverage the redundancy in the program to exercise behavior that's somewhat similar to what a test would exercise, right? We'd of course need proper language level mechanisms to capture such errors and propagate them to the appropriate software layers for handling. Yeah, so that was my bit. I think David is going to take over. Maybe I should unshare. David, is that easier for you, or?
We'll see. Okay, cool. So I'm going to talk a little bit here about how we're thinking right now, at least, about mitigating SDCs both in software, and then a little bit about the security angle on these things as well. I'm a security researcher, and so that's how I think about these types of problems. The first and kind of most straightforward way we can think about solving this type of problem in software, and we're at the point now where we're assuming we have failed to detect that this core is mercurial, it's going to manifest errors in some way, and we would like our computations to either be able to recover from these errors or at the very least detect that these errors are occurring. And so we can use redundancy, right? This is relatively straightforward. We're going to do something like triple modular redundancy. If we want to do something like add two vectors in our program, in our workload, we can shard this out. Those shards can then all run the exact same computation across different nodes. Now, a node in this context might be two different ALUs on the exact same core. It might be two different cores on the same platform, or it might be two different, entirely different nodes, like in your rack or in your data center. That's kind of a separate set of decisions about what you think your failure modes are going to look like. But you compute this out, you do 6 additions, you get a vote for majority, and as long as you don't have a majority of your nodes have the same failure, you at least know you got an error, and you've probably been able to recover and end up with a correct computation. But that's a lot of additional computation. So we can maybe do better, which is that we can adopt ideas from error correction, right? And so we can do things like Reed-Solomon encoding. And so in this case, what we're going to do is we're going to do the same type of addition that we were doing before, but instead of having every new node do the same computation, we're going to generate a bunch of code words. You do this by using your x's as coefficients to polynomials. You generate one of these code words with different alphas for each of these. And you end up with a whole bunch of these x primes and y primes. And then each of your nodes does one addition. It adds one pair of x primes and y primes. You take all of these, and then you're able to then perform your ECC decode operation. And you get back the result that you wanted in this case. But you can also correct some subset of errors. In this case, we can actually tolerate one of our nodes having some amount of error. So this is great. We can do something ostensibly a little bit better. And we can talk about comparing these, right? Like, do we want to generalize this approach? So for our vector addition, if we're doing just straightforward redundancy, we're talking about tolerating one corrupted node out of 3. And we're getting 6 additions that we have to do to guarantee 2 correct additions. And this scales linearly, which is not ideal. But it's straightforward. Whereas in the encoding case, we actually do a little bit better. We're tolerating one corrupted node out of 4 nodes, but we only did one addition on each of our nodes. Now, we do need to do encode and decode, so that's not free, but that means that we're able to scale this out. So if we expect that we have an application that has a very large amount of parallelism or a lot of vector operations, we can do this type of encoding, and then we can spread it out over a large number of nodes. We tolerate corruption at a relatively low number, but we can tune all of these parameters. And you only need to do then across your nodes n additions to guarantee n-2 correct additions. So if we have these types of approaches, the question becomes then, how do we choose them and how do we tune them? And I come at this, as I said, from a security perspective. And so my question is, what do we need to be drawing our lessons about? What our errors are going to look like when an adversary gets a hold of them? And the analogy that I'm going to draw here is to the Rowhammer series of work. This really got started in about 2014 with some observations about the fact that an adversarially structured DRAM workload will induce disturbance errors in that DRAM, and those errors are non-correctable. You're not going to be able to necessarily see them. Your values have just changed. And the security community got a hold of this and discovered that they could abuse this in servers, they could abuse this in clouds, they could abuse this in edge, they could abuse this in IoT devices, in browsers. It just kind of went on and on. And this is neat, and this is somewhat interesting because it's the one really well-studied hardware error that is software induced that the security community has managed to spend time on. And so we should draw what lessons from that we can about what will happen if the adversaries start using SDCs in cloud infrastructure. And so what we need to do is we need to get back to fail-stop detection. And I say that because the lesson we've learned from Rowhammer is that reliability failures do not look like adversarial failures. They are completely different from each other. And I say that because we can look at something like ECC, like SecDed in our RAM, as an example. When Rowhammer was first discovered, a natural response was, we have error correction in server DRAM. We don't have it in edge DRAM, but servers are going to be fine. It's going to be OK. The answer is, yeah, this was really good at stopping random error that you get from your high-energy particles coming through your atmosphere and flipping your bits. And it's absolutely terrible at correcting adversarial error, because the adversary does not randomly distribute its errors across your DRAM. It focuses them and overwhelms your ECC, and in fact would overwhelm the ECC scheme's ability to even detect that it had errors. So it's not just overwhelming the correction capabilities, it's overwhelming the detection capabilities. So if we're going to tune the software mechanisms that we're building to tolerate errors, we need to make sure we're tuning their detection capacity to at least what we know the adversary's maximum capacity is. Our error correction capacity can be lower because that's more expensive, but our detection capacity needs to be scaled. There's also an interesting lesson here in how we build these mechanisms. One of the responses to Rowhammer was a series of mitigations called targeted row refresh, which attempted to stop errors from ever occurring rather than correct or detect them. This wasn't really built with conversation with the way that the adversary actually interacts with DRAM. And it was an effective scheme until people reverse engineered how it worked. And then it stopped working completely. And so I think we need to be extremely careful when we approach this with the way that we sometimes think about this in terms of we know what our workloads look like. Like if we're a cloud vendor or a hardware vendor, we say, we know what our workloads operate like. We can run them through this. We use these as our test vectors. That's wonderful. That's not what your adversary is running. And so your adversary knows your reliability limits. You build your systems so that your correction mechanisms and your detection mechanisms with that in mind. So the last piece here is going to tie it back to kind of what I was saying about why I'm really big on understanding the security impacts of SDCs. If we know what our adversary is going to do and we know what their objectives are, then we can build effective mitigation techniques into our platforms. And again, drawing on Rowhammer, because as I said, it's the case that we have of what has happened. We know that Rowhammer corrupts victim programs. This is a relatively clear security violation. It's an integrity violation. If we have systems where the adversary workload runs co-resident with a victim workload, and the adversary can corrupt the victim program, okay, what we do is we build redundancy, we build error checking into the victim program, we have platform level detection of errors and correction of errors, and that's wonderful. But there's another set of things that people did with these techniques, which is that they violated confidentiality. There's a set of work that discovered that they could use the Rowhammer effects to read victim program memory in such a way that, in fact, ECC corrected all of the errors. So the platform believes that it has caught and corrected every error that occurred in the system. You are going to get back a report that says, like, yes, our error correction capacity was sufficient, we've done everything we've needed to, and yet your victim workload's confidentiality has been violated. So we need to be detecting our errors at the platform level, and we need to, again, fail-stop behavior when we can for safety. And we also need to understand our adversary's goals. This will let us detect when people are abusing SDCs. Again, there's one really cool example here that we can draw upon, which is the bit squatting work that came out a number of years ago. And it's an observation that if you look at the DNS traffic across a large enough data center, you will see that you have DNS requests flowing out of that data center whose ASCII representation of the name being requested is 1 bit off from the name they were trying to request. But what's interesting about these packets is that their checksums are correct, which means that the error occurred like somewhere in the application and a bit flipped in the name, and now the application is requesting it. So all of your error detection below that layer is going to believe that everything's fine. But you have these erroneous connections going outbound, and what did people start doing? They started registering those DNS names. So if we know people are doing that, and we know that this is a potential problem, we can see it in the network, right? This is why we need to know what they're doing. So there's a couple efforts that we're starting to pursue and starting to look at, and this is where we'll close out. We're working on inferring, as Baris said, what instructions might be faulty. We care about knowing that because, again, it informs us both what we need to be protecting with either software transformation, or it will also inform us what an adversary might do with those faulty instructions. And we're doing it with things like looking at silly fuzz and looking at Intel's DC diag tools, and then trying to draw insights from those to build more agile tools. And then lastly, as I said, we need to understand what the meaningful adversary objectives are in this space. And this will depend on whether victims and adversaries share and co-locate with each other, and where the adversary's viewpoint in the network is. With that, I'm happy to take, I think we have a minute or two for questions, but yeah?
When we lose security, maintaining performance isolation between VMs is hard enough. We can't even maintain security isolation. That's a problem.
Yeah, I think we've kind of, we've not had a chance to look at what the fact that we're pushing to a world where we're going to see errors propagating in more of our hardware stack than we have been, and we haven't gotten a chance to kind of evaluate what that means.
So you use Rowhammer as an example here. Rowhammer is something where there is direct sort of attacks between memory spaces possible. But so these material cores, do you think similarly they may be leaking information, or is that more of a...
Yeah, absolutely. So there's a couple cases they can fail. So if the way that they're failing is in cryptographic routines, this is catastrophic. We know that there's lots of good cryptographic work out there that shows, or cryptanalytic work that shows, if you have a single bit flip in a key, then during a computation, a single ciphertext is enough to do key recovery. And so that's not great there. More than that, though, is that the thing that interests me specifically about bit squatting and other things like it is it means that we may be leaking to our adversaries which of our cores are mercurial, right? If I, as the adversary, have a network vantage point, and I can see that there are some packets coming out of these machines that have unexpected results in them, especially if I'm the person who sent workloads to that machine, now I know that core is mercurial, or potentially mercurial, and I can start to narrow in on what I can make it do. So.
My experience has been, I don't think I've seen a mercurial core. I've seen mercurial network switches. So we have certainly detected bit flips in packets in various places, and so far it's always been from the switch. But that's not to say that it wouldn't be coming from force.
I think the two works out of Facebook and Google that Baris cited are actually really good examples. For us, those were illuminating that the error rates were that high.
There's another organization I'm familiar with where they're seeing uncorrected errors once a day.
Yep.
So those are errors where enough bits flipped that the error correcting memory did not notice it.
Yeah,
so once a day across their fleet, which is very high.
And that's only going.
Yeah.
Okay, well, thank you.
Thanks.
Okay, so I'm Arvind Krishnamurthy. I work on networks and distributed systems. Very far away from accelerators in general. I'm one of those people who like both BGP and Paxos. And what that really means is that oftentimes what I end up doing is looking at any problem that comes up from a networking angle or a distributed systems angle. So I'm going to corrupt accelerators from a networking and distributed systems perspective. So the thing which I want to talk about the various trends that we're seeing in the data centers, and in particular with accelerators. And what was pretty interesting was one of the talks from earlier on in the day really set up most of the things that I'm going to be talking about, which is this increasing degrees of specialization which is happening inside of the data center. And so specialized hardware is actually being used for a wide range of use cases. It's used for improving performance. It's used for increasing energy efficiency. It's used for reducing cost. And they come in both small and big packages. That is, oftentimes we think of accelerators as GPUs and TPUs, which are these big ones. But they're actually these small accelerators which are kind of spread or sprinkled across various different devices, from smart NICs to programmable switches and so on and so forth. So it's kind of nice to have that perspective that it's actually this wide range of accelerators that we are actually dealing with inside the data center. So the canonical examples are really the AI accelerators. Of course, you have domain-specific accelerators, such as video transcoding, which Google has. And now we have interesting other things which are coming up, such as computational SSDs, which have some amount of compute power along with the SSDs. And of course, you have wire-level kind of communication accelerators. That is, smart NICs typically now come with various interesting hardware blocks for encryption and compression and all of those different things. So that's one trend. The other trend is that what that's enabling is actually this push towards disaggregation, which is essentially being able to take away these accelerators and being able to consolidate them in its own set of tiers, and which primarily comes from what that enables is that you have a scheduling problem, which in some sense could be easier, which could reduce the amount of resource stranding that you might have in your clusters. And it also enables independent scaling of the various different entities that you have in your system, compute entities, accelerator tiers, and so on and so forth. It also means that you can have immediate adoption of new technologies. You just roll out a new cluster or a new rack of new accelerators, and suddenly you have access to those technologies. But that also means that you have cluster-wide heterogeneity across the data center. Another trend, and this is where my networking angle comes from, is that we have to think about networking as sort of a first-class consideration when we talk about these accelerators. So what I mean by that is that networking is an enabler in certain ways. That is, you have essentially deployments where a smart NIC-based headless entities, which are JBODs or JBOFs or whatever you might call, which allows you to enable sort of large deployments of accelerators with very low very low energy cost and at very low cost in some sense. So that's one place where networking ties in. The other place where networking ties in is that oftentimes it's a smart NIC or any one of these programmable network element also provides a platform for deploying accelerators along with it. That is, I'm actually building a smart NIC. I have some amount of space area which comes with it. I'm going to deploy some accelerators along with it, which are useful for wireline communications, which might go through that smart NIC. And the third thing which is interesting here is that we have these new interconnects such as CXL, which Simon kind of talked about, which is now going to enable sort of these rack scale deployments which have very tight coupling. And this is another piece which is really interesting, which is that in general, we have kind of built data centers with loose coupling of resources, which is really nice in an Ethernet-based kind of communication paradigm. But now with these emerging interconnects, you should be thinking of sort of more tight coupling between compute elements and accelerators and various other elements in your system. And then finally, this is where Zach's work really comes in, which is that these accelerators come with a proliferation of APIs and data types and all of those different things. And the only way you're going to get maximal efficiency out of them is actually if you can actually take advantage of the specific capabilities of every accelerator that you actually deal with. But oftentimes, those capabilities are actually hidden behind sort of libraries, opaque libraries, and so on. So what we need is actually a compilation kind of system which can actually kind of dig through it so that we can enable specific optimizations, such as specific numerics or specific sort of tensor representations and things of that sort. So that's the context in which we are proposing to do the work. The outlook for data centers is that it's going to be it's a changing world. Both the edge and the data center will increasingly involve distributed systems of heterogeneous accelerators. And these are going to be really moving away from a server-centric world to potentially one which at least servers are equally matched with various kinds of accelerators in the data center. And as an example, if you were to, for instance, say that a request comes in for Google, it might go through a video transcoding unit. It might go through various SmartNIC-based accelerations along the way. It might then end up hitting a TPU or a GPU. So it's multiple different accelerators will be required for speeding up a single application. And they will communicate across and span different types of networks. So we could think of the server as a hub, which connects Ethernet-style networks with local interconnects, which might be at the cluster scale. And we'll have to, of course, support multi-tenant workloads. That's of course, a given. So the goal of this thrust is essentially two aspects to it, which is we need distributed systems to manage, compose, and utilize these accelerator tiers. And we also need to, and you can really think of that as the higher level scheduling problem. And then there's kind of a lower level scheduling problem, which is for really tight coupling and so on, which is that we need compilers to help adapt and optimize existing workloads to these new systems. So with that, so let me actually say, it really opens up a huge set of challenges. That is, how do you achieve a high utilization is clearly one challenge. How do you have fairness when you actually have shared resources in your accelerator tiers, which have to support multi-tenant workloads? And how do you sort of enable sort of low latency networking so that you can actually sort of reduce the cost of disaggregation in some sense? How do you bridge different types of networks together in a seamless fashion? How do you have fully functional stacks on standalone accelerators? And Tom has some very interesting initial work in that space. How do you exploit on-path acceleration? How do you split tasks across different accelerators? How do you do malleable compute placement? The same amount of compute actually can be done at different places now. How do you choose, and how do you actually move things around as the workloads change and for different applications? And how do you accommodate multiple generations of accelerators? So there's a whole lot of challenges. Yeah.
So the first one makes perfect sense. The last one also is pretty critical, which is how you accommodate multiple generations. Second one is interesting. Why is fairness important? Because I think you're paying for some amount of these resources, right? Like you get what you pay for in some sense. Why is fairness a critical dimension here?
I think the way I think about it is that this is actually sort of maybe I feel cloud systems don't. For instance, if clearly Microsoft and Google have disaggregated storage systems. What kind of guarantees does the disaggregated storage system give to multiple tenants who are accessing the same device at a given point in time?
I propose maybe it's not the word fair, but it's deterministic.
Predictable performance.
And in particular, you don't want an attacker to be able to get more than what the system wants to allocate.
Yeah. Well said. So predictable performance may be equal slices or something along this. Quality of service would be another way of thinking about it. Yeah.
Besides those canonical functions you listed, what other function are you envisioning with the accelerator?
Sorry, can you repeat that?
You listed some canonical
accelerators.
Like an accelerator, right?
Yeah.
Besides those,
right.
What are some examples that you envision with an accelerator?
That's a great question. I think Thomas Venish might be able to answer that question more than better.
I would ask the same question. Everybody says there's going to be lots of accelerators. The question I always ask is, identify one. It's not TPU. It's not video.
Hold on to the next slide. Then. Yeah, encryption and compression. So that's kind of what I mean. That's one of the things which I wanted to set up, which is that we have small accelerators and big accelerators. And
you're painting a vision. You'll be swimming in accelerators. Okay, it could be an engine. what are we going to accelerate?
Why did you wait for a slide or two? And I'm actually going to talk through some of those examples. So the thing is, of course, that large laundry list of research problems, it's very hard to sort of make progress on it in abstract. But instead, what we're planning to do is to have a focused exploration, which takes two use cases. One is programmable disaggregated storage, is the one that I'm going to sort of call the first use case. And the other one is disaggregated ML inference is the second use case. And we can kind of walk through what it means. And even if we were to actually build very efficient systems for these two use cases, that itself would be a contribution. But the hope is that we would get lessons, that we would learn lessons from doing this so that it actually would apply to managing accelerator tiers in general. So the setting here is that disaggregated storage has been in use for the last 10 years, maybe, say, for instance, at Microsoft and Google. And but what's new now is that there's ability to perform various bits of programmability in accessing this disaggregated storage. So that is, I can sort of push compute a bit closer to where the storage is. As part of the data ingestion pathway, you can actually perform some various interesting tasks. You can also do compression, encryption, and various different things along the path. And you can also provide these various QoS properties or predictable storage access properties also along the path. So, and here now the elements, and this might address some of the things that you're talking about, which is that the way I think about in this setting is that SmartNICs, network accelerators, programmable switches, computational storage, all of these are kind of the accelerators in some sense that I'm going to take advantage of in building such a system. And the goal is to provide end-to-end programmability and control for disaggregated storage systems. I want allow applications to specify computations that can be performed anywhere as part of the access path, enable higher level abstractions. That is, I can simply say that I want an elastic SSD, which kind of spans multiple servers or multiple JBOFs, and that can scale based on what the workload is. Exploit new storage innovations. There's kind of interesting kinds of SSDs which are coming about. Integrate those storage innovations as part of this. And of course, as I said, achieve better QoS and efficiency and load balancing and so on. So here's, for instance, would be an example of how that would play out. That is, the programmer comes and says, here's the set of computations that I would like to perform on every piece of data which is being accessed as part of this disaggregated storage. That gets sprayed across SmartNICs, network accelerator cards, programmable switches, and on the actual target side, which might include computational SSDs, which are housed within a SmartNIC, which is actually serving as a headless deployment entity, which is energy efficient as a consequence. And each one of these things have different strengths and different capabilities in terms of what kind of computations it can do and how it can, what is the performance energy kind of balance that it might provide. So that's one such example. There's a whole bunch of research that we can do there. Another example is disaggregated ML inference. Here, the goal would be to build serving systems that kind of sort of address the needs of emerging ML applications, where what I mean the needs are is you have huge heterogeneity in terms of memory requirements, CPU requirements, and XPU needs. And you have sort of, you need to be able to perform multi-node execution to provide an application level logic, which is higher level than just simply executing specific models such as ResNet or something of that sort. Rather, you might want to actually say, I'm going to look at a traffic camera feed. I'm going to be able to actually look at, first do object detection, for instance, using one particular model, and then I can do face detection using a different model. You can do car detection using a different model. And all of that is actually expressed in some sort of a high-level abstract sort of language, which kind of describes the sequence of operations which have to be done. And in particular, many of these things might have very high resource needs. You might want to target both latency-sensitive inference as well as throughput-sensitive inference in the case of batch processing. And there's huge diverse set of accelerators and diverse set of interconnections that you want to take advantage of. Here I want to actually mention that, if I look at things such as Grace Hopper and so on and so forth, which has very tight coupling between the host and the GPU unit, that's, they use NVLink, but, some version of CXL could actually replace that, and there could be very interesting use cases there. So in this case, again, if I'm actually using throughput sensitive processing, I'll be streaming in data potentially from computational SSDs, going through SmartNICs, goes through high memory equipped server, which is used for storing embedding tables, which are gigabytes of data, which is small amount of compute but very large amount of memory which has to be performed, and then it goes through an XPU, and a different code path through your application will actually go through a different XPU, which is actually suited for that particular model needs. And then before eventually it hits an FPGA, which kind of maybe aggregates all of the data in providing, and you might want to provide end-to-end SLO latency constraints across all of this. And again, there's a whole bunch of research to be done in that space. But the thing which I want to say is that all of this is looking at the big sort of runtime level distributed systems issues. But there's actually a lower level short time scale compile time issues which also have to be addressed. And that's where Zach's work comes in.
Oh, wow, already a question. This is...
Sorry, I was curious, very nice talk. I was curious about your take on the networking fabric that connects these accelerators. Do you think that along with a proliferation of accelerators, there should also be a proliferation of some boutique networks connecting these accelerators? Or do you think, Ethernet is good enough?
I think my hope is that there will be some very interesting networks connecting these. I mean, at this point in time, I think a lot of ML applications don't need boutique networks. You can actually fire off maybe coarse-grained computations which are running on the accelerator, and that's something which is, which will run for maybe a millisecond or maybe a few hundreds of microseconds, a few milliseconds potentially. But if my sense is that we will at some point start building ML applications which will require very tight coupling between the capabilities of what the host has to provide and what the XPU has to provide. And at that point in time, I think there will be some, in fact, actually, I think NVIDIA claims that the Grace Hopper, which is has a very low latency, potentially cache coherent interconnect, I think they demonstrate performance benefits in some workloads, which I don't quite understand myself. But my sense is that we will have such ML workloads in the future. And that's really where actually a lot of Zach's work might also help.
Yeah, I think to some degree it also depends on what level, right? So on the network, I completely defer to Arvind. I mean, I think if you're talking about on chip, then there are really interesting questions about, for example, with ML workloads, a lot of times you have some bit width and you typically use that for your scalar size, but that's a bummer because you're doing a bunch of max and you want your accumulators to be twice as wide at least for overflow issues. So that's not reflected in current, DSP designs on FPGAs and stuff, right? I'm losing a lot of accuracy, and now I am forced to make these hard choices about, well, when am I going to go off device? Because as soon as I do, I'm going to lose something from the accumulator, right? If I leave this device. So I think there are a lot of interesting design decisions there. But this is largely because there's this sort of big, exciting revolution, right? And it's true because Chris Latner said it. And not only did Chris Latner say it, he was citing Hennessy and Patterson, right? So there's going to be a ton of you can't be wrong, right? It's got to happen. I know this is your question. Where is it, right? This is what you're thinking. Oh, we're done. Oh, okay, never mind. Now everybody's on board. I do think this is a great question, though. Where are these things coming from? I think maybe after this deck, dig into that a little bit. But there are a ton of challenges, right? So even if we have a lot of really great hardware widgets, we have to somehow use them, right? You have to somehow map your workload down to exploit those devices. And right now in practice, this is hard from both directions. So if I think about how I'm going to expose that hardware up to the application, here's an example from Accelerator at Harvard named FlexASR that does entire LSTM layers in the accelerator. And this kind of code is not very fun to write. So what we do is we hide it behind a library, but then I have to go back to my application, and anywhere I wanted to do this layer reduction, I have to go drop in a call to this library. Well, that's a bummer because there's a lot of code that's already been written. Are we going to really go back and add these little library tweaks in everywhere for every application? What if I have a slightly different accelerator? What if I have 10 options, right? Like, this is going to be a super big pain. But the pain also happens in the other direction. When I'm trying to build an accelerator, I'm thinking about the operations that software wants. Right? Now, it's really hard to design and build an accelerator. So typically what I'm going to do is think about it in terms of that operation. I'm going to say, oh, here's what the host CPU version does. I'm going to make a version in hardware whose accuracy is very similar, but it's way faster. It's like 99% accurate. Well, the problem is if you only think about operator granularity, when you go up to full applications, things like numerical accuracy can go out the window. But that's really hard to see if you're just thinking about it per operator. Now, this is an example of a Lorenz attractor, which is a classically chaotic system. There aren't a lot of Lorenz attractor accelerators out there yet. I'm not sure that's a growth market for customization. But we'll see an example here in a few slides where these same kinds of numerical challenges do arise, for example, when you go to ML accelerators and try to map actual applications. So what's going on? Well, it's really hard today to deploy an accelerated application, in large part because it takes a lot of different skill sets all working together. And there's a bunch of challenges with data type design, a bunch of challenges with the hardware design, getting faster simulators, and being able to simulate full applications end to end. What I really want to focus on is this kind of middle task. We want to figure out, given an application, when and where can I exploit available hardware? And we want to do this in a largely automated way that allows to adapt to changes in the environment as new accelerators come online, or even dynamically, if a big job comes in that takes away some of the resources I thought I was going to have available. And the way we want to pull that off is by thinking about this as a compilation challenge. So I want to be able to think about the set of accelerators I have available as instruction selection, right? Like I have this number of these accelerators. How do I adapt my workload to take advantage of those? And there's a bunch of benefits to this approach. It'll hopefully make it a lot easier to deploy. It also facilitate when I'm designing accelerators because it'll be a lot easier to test applications against the prototype accelerator. And ultimately, the real vision would be able to build applications that are sort of omnivorous in the sense that they can consume whatever resources are available in the environment they find themselves executing. I think that kind of flexibility will be really important and provide a lot of opportunities for scheduling, especially when we have these workloads moving from mobile to edge to cloud and back and forth. So one example of how we've been building this is in the machine learning domain. And in this case, what we're going to do is we're going to take a model and a description of a set of available accelerators and find a set of potential mappings from that workload to the accelerators. And then we'll be able to pick one out. And because we have these sort of uniform interfaces, we can automatically do the code gen. Now, the key technology that makes this possible, I want to spend just a couple minutes showing you, is called equality saturation. So this is a compilation technique that we've been developing here. It actually started, I don't know, Adrian, if you remember, back, Ross Tate and I did some of this in 2009. But for the past couple of years, this has really taken off from our group. And it's a different take on the traditional compilation approach. So normally, when you're building a compiler, you start with some source program. And then you apply some fixed sequence of transformations, or nearly fixed sequence of transformations, to get the final version of the program you want to run. Now, this is not super flexible. You're going to end up with like a bunch of pragmas and ifs and pound defines in order to make this more robust. Instead, what equality saturation does is try to answer this question, what if I had applied transformations in a different order, or different transformations? And so we start with that same input program. What we're going to do is represent an entire space of different implementation strategies. And the key here is that we represent the whole space. We don't commit to specific transformations too early. So when I'm trying to decide, like, oh, should I do common sub-expression elimination now? Or should I like fuse this operator here? Or should I wait later and then try to schedule it? I just note that these are all valid choices. And I can wait until later to decide which is best after I've seen what the fallout, what the consequences of that optimization strategy might be. So I can sort of pluck my favorite version of the program out at the very end. So this kind of sounds like magic, right? Like, how are you actually going to simulate applying all rewrites in every order? That sort of is obviously an explosive problem. But we have some fancy tricks up our sleeve that I can't get into right now. But at a high level, we sort of steal some technology from inside of satisfiability modular theories, SMT solvers. The other SMT, the non-hardware, the logic SMT, the other kind of logic SMT that allow us to represent these huge design spaces very compactly and apply transformations over them. So we've actually built a prototype of this already for on top of TVM using egg. And what we're able to do is take a sort of uniform description of an accelerator interface and find many opportunities to invoke that accelerator for given different models. One of the things that I'm really excited about is this line here about M to call. So there's a bunch of classic sort of data swizzling transformations that you have to apply in order to get your tensors to look like the right shape the accelerator wants. And what's neat is that with this technique, we're sort of searching the space of available transformations. Those just fall out for free. So this implementation, our prototype flexible matching compiler, does things like M to call, even though we never wrote an M to call transformation. It just emerges as a consequence of searching that entire space of implementation strategies. Oh yeah.
So what is the criteria for saying that this program P prime is actually better than P double prime? I mean, how do you rank it?
That's a great question. So I have a couple slides about this, but I mean, there's a lot of different ways you can extract a program out of this space. So essentially, you can have just a cost model, and you can argmin, like find the smallest the program which minimizes that cost. There are some limitations because of the way these are represented, but I'll show some examples that I hope will convince you that it's quite expressive, the range of things we can support.
Sequence of transfer, you're exploring paths, right?
Yeah.
So that means, is it like a genetic algorithm or like some fitness function that you're chasing to sort of like?
So the exploration can be, but usually we actually don't make it cost guided. We just explore as much of the space as we can. And we don't worry about cost until after we've represented an enormous design space. Then at that point, we come back and extract. But there's a lot more to say there. So I'll show a couple of examples, but I'd love to chat more offline about how the extraction works. And actually, one of them is you can use genetic algorithms actually to guide extraction. That's something we did, of all things, when we applied this technique to carpentry. But that's a whole other story. Anyway, so we built this prototype. And one of the things that was neat about it is that we could take prototype accelerators and actually run them on applications end-to-end for the first time. So we already talked about FlexASR. We run it on a natural language processing model that it was designed for. It produced results very close to the reference. We took another prototype accelerator, HLS-CNN, which is a convolutional neural network. It does convolutions for like vision models to accelerate those. And we compiled Resident MobileNet with that. One thing I didn't mention, sorry, I'm trying to hustle because I know we're a little over time. Here's a really cool thing about this approach. Past techniques for mapping applications down to accelerators are often very committed to this like single host, single accelerator worldview, right? Like I know how to run on the CPU. You've told me this accelerator is now available. I'm going to try to take advantage of that one accelerator. What's neat here is that for free, we can actually take advantage of multiple accelerators. And that also gets very interesting because what if using one accelerator prevents use of a different one that sort of overlaps? This all gets figured out. So in particular, with this ResNet and MobileNet example, when you're using multiple accelerators, the results from simulation were way, way worse than the reference, right? But the designers didn't know that because they'd never been able to run end-to-end because they didn't have compiler support. And it was too hard to go in and modify the applications to get those results. And then using results from this, they were able to debug their designs, fix the hardware, and restore accuracy very close to the reference model. So there's a bunch of other things here. We're talking about cost functions. One thing is to actually look more at optimizing for distributed data movement between accelerators. So it gets more interesting when things aren't sharing the same memory. Another thing we've been looking at is a technique to make it very easy to compile to FPGAs. Anybody who's used existing hardware synthesis toolchains is familiar with the wailing and pain and gnashing of teeth that arise when you're trying to figure out how to map a given design onto the available LUTs, carry chains, DSPs, etc. on FPGAs. The current approach doesn't scale super well. It turns out we can use this technique of equality saturation here too. Happy to chat about it more offline. We've also people have been using this technology even at the ASIC level. So getting back to the cost function, it turns out that some of our friends inside of Intel are using a quality saturation to do data path optimization for various graphics accelerators. And they can optimize their designs with respect to area or delay. And what's actually really neat is, so that's two fairly rich cost functions because you're thinking about the actual circuit layout. But what's actually neat is that you don't just have to pick one best program out of the eGraph when you're done optimizing. You can actually walk and create a Pareto curve, right? So you can have a space of trade-offs. And I think this is really exciting for scheduling, right? Lifting this idea back up from the ASIC level closer to the application. You can imagine essentially doing one compilation, extracting the curve, and then as my environment changes, I already have a plan for how to adapt and execute with different trade-offs, or my quality, my QoE requirements change, right? I know where to move on this curve to get the optimal trade-off ahead of time, and I can have that plan sort of locked and loaded. So I'm super excited about equality saturation, especially with applications to accelerators, making them much easier to deploy, making them much more adaptive and easier to, responsive to changes in available accelerators. And I think it fits really well with a lot of challenges Arvind was talking about for how do we support disaggregated accelerators across the data center, how do we support inference, et cetera. So sorry, I know I went a few minutes over and I was talking really fast. It's a little bit dim. It's the end of the day. But really happy to take any questions and talk more about ECSAT or accelerators if folks are curious. One thing I did want to mention, because there was this great question about where are all the accelerators? And I think there's a bit of a gridlock. So I was talking to Carlos Diaz from TSMC. And he keeps asking, he's like, we can make anything. Tell us what to make. Like, what device? Like, what new little device block of transistors could I make that would make your applications great? And then, on the compiler side, we talked to hardware people who are like, what do you got? Where's the accelerator? Like, I'll make my application so fast, and I'll figure out how to compile all of it. So I think there's a little bit where everybody's trying to pull from each other. And so I think that's sort of making it initially a little bit tricky.
You forgot the poor application developer. He has that information.
Yeah. So I think that one thing that would be great would be to figure out how to pull that out. So.
You get all of them.
Yeah.
Let's take a break.